Hello, hi, my name is Raj Narigotu. This is my thesis project. The title of the project is Enhancing Plant Disease Classification Through Unsupervised Domain Adaptation. The problem statement for this is that, as we know in agriculture, the AI adaptation is not that great as compared to other domains. So it's due to there is a big challenge when it comes to disease detection in the agriculture. Uh, the challenge is that the domain shift between the images which the models are being trained on and the images which the models will be used on. So because the models will be trained on lab quality images, but they will be tested in the real world where the quality and the domain is there is a great shift in domain. So because of this, the accuracy of the models is reduced, and this is classification is the accuracy of the classification is less, so which makes the models are not very useful in the agriculture. So my research question is, how can unsupervised domain adaptation techniques improve AI-based plant disease classification, enabling models to generalize effectively across diverse environmental conditions without requiring labeled real-world data? So by implementing these models, we would be expecting the models to perform better, even if the models are trained on lab quality images, but the we expect them to perform better on real world images. So with this research question, I'm trying to see how these techniques could improve the accuracy of the models and whether it is really possible or not. So the objective is to evaluate the model, implement the techniques, UDA techniques such as cycle GAN, SimCLR, pseudo labeling in a unified pipeline. So which means one after the others we will be implementing it, and after that we will analyze their performance gains after each technique. So we will train and test the model after implementing each technique, and then we'll compare if there is any gains in the accuracy or not, and if there are any limitations. I have used two data sets. One is Plant Village, which is like a lab quality images. This will be worked as a training data set, and then we will use Plant Doc, which will work as a target. So the performance metrics used for this is accuracy, precision, recall, F1 score, and TSNE. So moving on to the data set, as I said, we have two data sets, Plant Village and Plant Doc. The first one is the Plant Village data set. As you can see, it is a lab quality with the background, nice background, good lighting, and only single leaf is there. The second set is that this is a Plant Doc data set, which has a lot of background noise, and there are multiple leaves in it, and the lighting just could vary from one image to other. So we have taken these two data sets for our project. So the UDA pipeline is that we will first test it on baseline model. And we will train and test the baseline model using as I said, the baseline model will be trained on plant village and tested on plant dog. And then we will implement cyclic and translation UDA technique. And then again, we will train and test. And then we will implement SimCLR feature learning. Again, we'll train and test. And then we'll move to pseudo labeling. And then we'll move to the final classifier. Where we will include all of these inputs from these UDA techniques. And we will train it, and then we will test it, and then we will check if there is any improvements in accuracy, when we are implementing these UDA techniques. So as I said, Cycle can would add a pixel level adaptation. So where we will translate these lab quality images to similar to plan doc style images, and then we will train the model. We will train the model with the original data set along with these translated images to see if there is any improvement in the accuracy after testing on plan doc. So as I mentioned here, I mentioned the pipeline and also these images like this is a plant village image after implementing the cycle GAN translation. So I would also give a quick look into the coding part as well, along with this. As we can see, here in phase zero, I have implemented the cleaning of the data sets where, plant village and plant doc has been cleaned, and also checked. There are multiple class. There is a class difference between these two data sets as well. So we have chosen only the classes which are similar in between these two data sets and removed the other classes which are not similar in between these two. So as part of the phase one, here we have trained the baseline model. Um, and trained the baseline model and tested here. And when it comes to CycleGAN, in the CycleGAN, the phase two, what we have done is we have translated plant village images into plant doc style images. So moving to the presentation, right? So yes. So after CycleGAN implemented, we will move to the SimCLR, where we will get the feature level adaptation to our models, right? So here we will um, extract the features from CycleGAN translated plant village images. This is like a contrastive learning with augmentations, right? So this model will learn the features in the images, so that we would get a feature level adaptation to the models. Now, in the previous CycleGAN model, we have a pixel level adaptation. Here in this, we will get the feature level adaptation, where this model will take the domain relevant features without the labels, right? So, and then moving on to pseudo labeling, and here previously we have got the pixel level and then the feature level. Now we will get the label level adaptation for the model. So what we do is that we will by taking the pre-trained SimCLR, we will extract we will implement that on the PlanDoc, subset of the PlanDoc data set, and we will without any labels, and then we will take that high confidence labeled data from PlanDoc and add it to the original data. So by giving the pseudo labels to it, so this way the model will get some peek into the origin, the real time images as well. So our hypothesis is that so this way the model could even perform better. But there is some risks, such as this, pseudo labeling would include, some label noise as well, so which we have to be careful with. So we would be merging this pseudo labels as well to the training data set, and then we would be moving to the final UDA pipeline, right? So here we would take all the inputs, all the three from all the three steps. We will take all the inputs like CycleGAN translate images and the features from SimCLR, and then the pseudo labeling from the pseudo label set, and then we will take it as a training into the model, and then we will test it on top of the plant out data set. So this way we would be expecting a better performance of the models of the model by end of it. So but when it comes to results, I would like to highlight that unfortunately, the results are not as expected, not according to the hypothesis which we have seen. So we have expected that the model will eventually gradually improve its performance after each UDA technique, but in fact, it worked against it. So after in the baseline model, the validation accuracy was good, but when it comes to test accuracy, it fell down to 27.81, right? And then after implementing CycleGAN translated images into the testing, you know, still, but there is no actually, in fact, instead of improving the accuracy, the accuracy actually fell down to 26.05 percentage, right? So there is no improvement at all. And then after implementing SimCLR, feature learning, and then adding it to the model, the performance further fell down to 21%. So because it could be because the pseudo labeling is not introduced yet with SimCLR. So and then the next step where we introduce pseudo labeled data into the training set, there is a slight improvement on top of the the 21%. So now it is improved to 23.08%, but it is still less compared to the baseline model, which is 27.81 percentage, right? So it could be because the pseudo label, introduced noise into it, right? And yeah, maybe because of that, the performance might fell down. But overall, we have not seen any improvement as we have hypothesized, right? So from these results, what we have seen is that there is still a large domain gap between the lab style images to the real world images. Just because we have made synthetic images using cyclic and translated, it doesn't make it equal to the real world images. We may change the angles, but in the real world images, we have a lot of other disturbances and noises, such as background, and sometimes it have multiple leaves in it. So this could add a lot of noise to it. And also on top of that, pseudo labeling, when we are doing pseudo labeling, it will also introduce noise to the training data as well. And because of that, there is a high need for diverse data. There is an imbalance between the classes as well inside the training data set. So for that to resolve that issue, we need a diverse data set, yeah, which is a real world data set, and we need to filter the data into the correct classes, right? Um, in conclusion, the UDA pipeline, though the overall efficiency accuracy has fell down after implementing these techniques, but there is a class level accuracy which has seen a little bit improvement after implementing the UDA techniques. So there is still a hope in this. We can improve the accuracy, but we need to have great amount of high quality field images, right? Um, so yeah, as I mentioned here, there is a high importance of field specific data, right? And my takeaways for researchers or practitioners is that though theoretically it says that after implementing each UDA technique there should be accuracy improvement in the model, but we should not go with that. So it highly depends on the class balance between these diseases, and also the quality of the images which we have for training and testing, and also uh, the quality of the images, and also there is a very less number of images in the data set, so we need even more images which are high quality, right? So we should not take the theoretical implementation as it is, because it is domain specific. It could change from domain to domain. Some domains would perform better by implementing these UDA techniques, but some other domains might not perform better, such as agriculture domains, right? So the future work is that we should use more efficient models, like efficient net, which would use high resolution, high resolution, and also we should use hybrid adaptation, like cyclic and plus adversarial methods such as DAN, um, right? And also we would for the inputs, we not only just images, we should also include multimodal inputs such as weather and soil data, and we should have large balanced field data set, as I mentioned previously. And for the companies which are developing applications to disease detection to help the farmers, they should be having on-device optimization models to improve the efficiency of these models. Right. Thank you so much for taking time. I've included my core files, and in the configuration manual, I also included a Google Drive link where it will take to the data sets and the saved models. All the pipeline will be there in it. I hope I covered everything. Thank you so much for your time.